Hello, Calculus 1 students. This is the second part of our review for our second midterm. My caution is the same as the first part. We will have different problems on our actual test. So make sure you study all of the materials I have in Canvas in addition to this sample test. Okay, well, this first question, we begin with integration. We have three indefinite intervals. 1a, well, I see an inside function, the natural log. More than that, I have multiple of its derivative in the integrand. This is substitution, where u is the natural log of t. du, we take the derivative. This is 1 over t dt. Well, you notice in my integral, I have exactly du. I have a 1 over t dt. So I'm ready to convert to an integral of u. Here, my power, this is a fifth root. So this is u to the 1/5 power and du. Now we integrate, we add a power and divide by the higher power plus c. Final step, we go back to t, but also we don't want to leave this fraction in the denominator. So I have 5 over 6 ln t to the 6 over 5 power plus c. This is my final answer here. Next question. Well, I have a sum of 3 terms, and when we have a sum of terms in an integral, we integrate term by term. None of this is substitution, but maybe this first term I will rewrite as a power. So we have an integral. This is 2x to the minus 5. Then I have minus 4 over the square root of 1 minus x squared. And then I have plus the square root of 11 dx. Okay, I'm ready to integrate here. First one, power rule. We add a power, minus 4, divide by the higher power. Then we put a minus. What's an antiderivative for 1 over the square root of 1 minus x squared? Well, this is the sine inverse. So we have minus 4 sine inverse of x. Next term is square root of 11. When we integrate a constant, we just get that constant times x. So here we will have square root of 11 times x. And then don't forget plus c. Let's see, I might make this a little bit smaller and simplify my answer just slightly. You notice this first term is negative 1 over 2, x to the minus 4. And then I have minus 4 sine inverse of x. And then I have plus the square root of 11 times x plus c. This is my final answer here. Okay, 1c, we see something inside of the cosine, and we have a multiple of its derivative in our integrand. This is substitution, where u is 4 to the x. Now du, we take the derivative. When we differentiate 4 to the x, we have 4 to the x times ln 4, and then multiply by dx. Now in this case, you see handed to me in my integral is not exactly du. In my integral, I have 4 to the x dx. This is 1 over an ln 4 times du. So I have calculated the multiplier here. It's 1 over ln 4, and this is an important step. Now I'm ready to convert to an integral of u. I have an integral. We have cosine u times 1 over ln 4 du. Now we integrate. The constant we can just write down, 1 over ln 4. When we integrate cosine, we get positive sine. Sine u plus c. Finally, we go back to x. So this is 1 over ln 4. The sine of 4 to the x plus c. This was substitution. Super fun. Next question. We are given a particle moving in the xy plane. We are given its position as a function of time, and we want to calculate the velocity, the slope of the tangent line, and the acceleration, but all at t equals 4. Great. First of all, let's calculate the velocity as a function of time. Well, maybe I'll write this above. You notice this is t minus 3 to the minus 2 power. This will help me when I use power rule. Here is power rule for derivatives. Okay. Well, to calculate velocity, we differentiate the first coordinate. We have minus 2 t minus 3 to the minus 3. And then we differentiate the second coordinate. We have 3/2 t to the 1/2. So this is velocity as a function of time. Now evaluate at 4. V of 4, this will be minus 2 times, well, 4 minus 3 is 1. So we have 1 to the negative 3. And then we have 3/2 times the square root of 4. Well, we need to simplify this. 1 to any power is 1, so we have minus 2. And then the square root of 4 is 2, so the second coordinate here is just 3. This is the velocity vector at time t equals 4. Now, slope of the tangent line to the trajectory. In fact, we have everything we need. Calculation-wise, we just need to realize this. We want dy dx evaluated at t equals 4. We know this is y prime of 4 divided by x prime of 4. But you see, here's y prime of 4, and here's x prime of 4. They're in my velocity vector, evaluated at 4. So I can just write down the ratio. This is 3 divided by minus 2, or negative 3/2. Okay, acceleration. Okay, we're going to be differentiating a second time. We take this vector, the velocity vector, and we differentiate. So the first coordinate here will be 6 t minus 3 to the minus 4 power. And then I'm going to have 3 over 4 t to the minus 1/2 power. This is my acceleration as a function of time. Now evaluate at t equals 4. Well, we have 6 times 1 to the minus 4. Then we have 3 over 4 times 1 divided by the square root of 4. Okay, this is 6. 1 divided by the square root of 4 is 1/2. So we have 3 over 4 times 1/2. This is 3 divided by 8. So this is my acceleration vector at time t equals 4. Next, we have multiple limits. And if we use L'Hopital, we need to clearly state where it is used. Show our work. Well, okay, let's look at this first one. This is a limit at 0. What happens when we try to evaluate at 0? Well, e to the 0 plus 2 minus 0 divided by cosine of 0. The question is this 0 over 0? If this is 0 over 0, this indeterminate form, then we use L'Hopital. But you notice it's not. Cosine of 0 is 1. E to the 0 is 1. I just get this. What we observe here is, in fact, this function is continuous at 0. And so the limit is, well, we've calculated it. The limit is 1 plus 2 over 1, which is 3. I did not use L'Hopital at all here. Next question. We want a limit as t approaches 0 on the right of t times ln of 2t. So we have to think about what's happening here. T is approaching 0. Natural log looks like this. Goes through the point 1, 0 and looks like this. This is approximately the shape of the natural log, but you notice as t approaches 0, well, the natural log goes to negative infinity. This is an indeterminate form, but it's not yet ready for L'Hopital. L'Hopital applies when we have 0 over 0 or plus or minus infinity over plus or minus infinity. And so we just need to rewrite this so we get the right kind of indeterminate form. What I can do, t goes to 0 on this side, I'll put the natural log in the numerator, and then I can do this. Now, properties of exponents, without a doubt, this and this, they're the same. But now if you think about what's happening, the numerator is going to minus infinity, And the denominator, well, this is a 1 over t in the denominator. And as t gets very, very small, coming from the right to 0, this goes to positive infinity. So this is what we wanted here. We may use L'Hopital. So this is where I mark LH. The first equal was not L'Hopital. I just rewrote my function. And L'Hopital says we take the derivative on the top. That would be 1 over t. We take the derivative on the bottom. This would be minus t to the minus 2. And then we reevaluate the limit. Well, it looks like we're getting something indeterminate again. It looks like we're getting another infinity over minus infinity. But we don't need to use L'Hopital a second time. What we need to do here is just use properties of algebra and exponents. So this will be a limit as t approaches 0 on the right. See this? If I move this to the numerator, it will be with a positive exponent. So really here I have a minus t squared divided by t, which, one more step, it's a limit as t approaches 0 of minus t. Oh, this is something I can evaluate. Negative t as t approaches 0. Well, this goes to 0. Maybe I'll put parentheses here. My answer is 0. This was a fun one. Definitely L'Hopital applied, but we had to do a little bit of work first. Now, last question on this limits problem. We want to limit as x goes to infinity of sine pi over 6 plus pi over x. This is, well, I'll do it in 2 steps, but this is a bring the limit inside a continuous function question. If we take this limit, well, you see this part approaches 0 because, well, the denominator is growing without bound, fixed numerator. So this just goes to pi over 6. The sign is continuous. And so the limit as x goes to infinity, sine of pi over 6 plus pi over x will be the sine pi over 6. Now, we can evaluate the sine of pi over 6. Sine of pi over 6 is 1/2. So this is our answer, 1/2. Number 4, we evaluate this definite integral. Show our work. Well, we see parentheses. More than that, the derivative of tan inverse is 1 over 1 plus x squared. So I'm going to use that here. My u is the tan inverse of x. du is here, 1 over 1 plus x squared. dx. Now you notice I have exactly du in my integral, but let's change our bounds. I always do this. I change my bounds to u bounds. So x ranges between 0 and 1. Here u will be the tan inverse of 0, which is 0. Here u will be the tan inverse of 1. Okay, if you don't know this one off the top of your head, this says the tangent is 1. And the angles between minus pi over 2 and pi over 2. Tangent is 1, so sine and cosine are equal. This happens at pi over 4. Okay, so here's what I will put in a box. My work for substitution. Now I'm ready to get back to my integral. This becomes an integral from 0 to pi over 4. We just have u squared du. Now integrate u cubed over 3. We evaluate between 0 and pi over 4. And we're almost there. We have pi over 4 cubed over 3 minus 0. So you see my answer. We have pi cubed divided by, well, it will be 4 cubed times 3, which, according to my calculator, is 192. This is my final answer here. Number 5, optimization. Okay, we have a closed circular cylinder, and we're given the volume. We want to find the radius r and height h such that it has the least amount of surface area. We can start by drawing a picture. we have h, we have r. Well, we are given the volume, so let's write that out. The volume, how do we calculate this? We take area of the base, which is pi r squared, and then multiply by the height. And we're told this is 16 pi. You notice this is an equation. This is my constraint equation. I am not trying to maximize or minimize volume. Say, this is given. Volume is fixed, 16 pi inches cubed. Now, we want the least amount of surface area. So we have a top and a bottom. The bottom is pi r squared. The top is pi r squared area. So the area of the top and bottom would be 2 pi r squared. And then we need the area of, well, the side. There's really one side. It goes all the way around like this. So how we get that area? Well, it would be the circumference times the height, because you could think about cutting and unrolling. This would be the height. This would be 2 pi r. So the area of the side that goes all the way around is 2 pi rh. And this is my objective function. This is what we want to minimize. Okay, we have our constraint equation. We have our objective function. That's usually the hardest 2 steps. Now, we take this and we solve for one variable in terms of the other. Let's solve for h in terms of r. Well, I can divide both sides by pi, and then I get h is 16 divided by r squared. Now, I can write my area as a function of r. What I want to do is substitute 16 over r squared in for the h. So I have 2 pi r squared plus 2 pi r and the h, which is 16 r to the minus 2. Let's simplify this. I have 2 pi r squared, and then I have plus 32 pi r to the minus 1. Okay, wonderful. We have a function. Oh, what's it defined on? Let's see. R certainly needs to be positive to make a cylinder, and similarly, h needs to be positive. But no matter how big I make r, I can find an h that works. So this is really defined on 0 to infinity, and we want to minimize. Now we're ready to look for critical points. We take the derivative. We have 4 pi r minus 32 pi r to the minus 2. Now we set this to 0. So 0 is a prime of r. Well, this would say that 4 pi r equals 32 pi r to the minus 2. You notice some really great things happen. You notice I can just divide by pi, then multiply both sides by r squared. Here I have r cubed, and divide both sides by 4. Here I have 8. And so you see, my radius is 2. Well, I have one critical point on my open interval, but I need to make sure this corresponds to a minimum. So let's do second derivative test here. The second derivative is 4 pi, and then we have plus, will be 64 pi r to the minus 3. We evaluate the second derivative at 2 is 4 pi plus 64 over 8, which is 8. So 4 pi plus 8 pi, which is certainly positive. And this says concave up. And then we look at this. This says we have a min at r equals 2. Final step, we read the question because I've done all the work, but I haven't filled in my answer blanks yet. So we reread the question. We want to find the radius r and height h. That's what we report back. In fact, the r we have, it's 2. Now the h, it's here. H will be, I'll write it here, 16 over 4, which is 4. This is this optimization question. Number 6, suppose f is differentiable. We want to find the derivative of h of x, which is the secant of f of x divided by log x to the 8 in terms of f and f prime. Do not simplify. Maybe I'll make a remark before I get started. You note that the log of x to the 8, first of all, what base is this? This is base 10. But moreover, I can bring the 8 out in front. So this is 8 log, and then I'll write the 10 so we see it. Okay, so I'm just going to use this because in particular I need to differentiate. And it's easier to use that log property first. Okay, now let's get started. We have one function divided by another. This will be quotient rule. So we have denominator, maybe I'll write it this way, log x to the 8 times derivative of the numerator. Here's where I'm going to have a lot to write. This is chain rule. My outside function is the secant. My inside function is here. It's f of x. So the derivative of secant is secant tangent. So we have secant tangent. Then we put in our entire inside function, which is f of x. F of x. Okay. Then multiply by the derivative of the inside function. That was chain rule. Denominator, derivative of the numerator, and then minus the numerator, secant of f of x, times derivative of the denominator. But because I have written log x to the 8 as 8 log x, that simplifies things. So the answer will be 8 over, we have x ln 10. That's the derivative of log of x to the 8. Now, denominator, derivative of the numerator, minus numerator, derivative of the denominator. And then quotient rule says all over denominator squared. So we put the log of x to the 8, and then we square it. It's a very big derivative because we had quotient rule together with the chain rule. Number 7, last question. We want a left Riemann sum for f of x is 5 to the 1 over x on the interval from 1 to 4 using 6 equally spaced subintervals. Well, if I call this A and I call this B, then I first calculate delta x. This will be B minus A divided by n. This is 1/2. Next step, we write down our partition. So I start with the left endpoint, march forward by delta x until I hit the right endpoint. So I have 1, I have 3 halves, 2, 5 halves, 3, 7 halves, and 4. Now, make sure we have 1, 2, 3, 4, 5, and 6 subintervals. You can also just count the points in your partition. You will always have one more point. So here I have 7 points in my partition. That makes 6 subintervals. So everything is great. Okay, next, the left Riemann sum. So I'm going to be using left, 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 and left, like this. Maybe I'll write it in summation notation first. This would be a sum. I equals 1 to 6. We would have f of x I minus 1 and delta x. I will typically factor out the delta x, so this is 1/2. Now, we evaluate. My function is 5 to the 1 over x. So this will be 5 to the 1 over 1 plus 5 to the 1 over 3 halves. Now, each time we have 1 over one of these fractions, we're really invert and multiply. So this is 5 to the 2/3. Oh. Plus, we have 5 to the 1 over 2. Plus, we have 5 to the 2 over 5. Plus, we have 5 to the 1 over 3. And finally, we have 5 to the 2 over 7. Okay, now, enter this one thing in your calculator in one big line. Let me do this in Desmos, and we will see what we get. This is what I have from Desmos. You see, I entered the entire thing as one line, then I round. We don't want to sort of round each of these and then round again at the end. We could have some big time rounding errors. So let's round now. We get 7 point to 4 decimal places. This would be 6788. This is this answer to this left Riemann sum. Okay, so this is the end of this second sample test. Thank you so much, students. Good luck on the second midterm.